All right, so this is chapter 5. Chapter 5 is really interesting. When the video should have gone over some of the lexicons used with it. That's not. I actually haven't checked the most recent version, but in the earlier versions they just started using. They didn't define it like ligand and substrate and stuff like that, which for chapter 5 and chapter 6, where it's really important. And so this one has to do with. This is really a continuation of chapter 4. It has to do with protein structure. And the textbook example that they like to look at, and in particular we're looking primarily at the quaternary interactions, but they like to compare and contrast myoglobin and hemoglobin. And so the thing is, myoglobin is just a single subunit. It's all alpha helical. It does have a heme in it, but it is identical to one of the subunits of hemoglobin, whereas hemoglobin has multiple subunits. They actually do the exact same thing. Of course, it's what the heme looks like. It's to bind iron, and in the bioavailable sense, it should be iron 2, okay? Because you don't want it to be iron 3, or you don't want it to be another metal ion, otherwise it wouldn't be good. And they call this the porphyrin ring, by the way, in case they say porphyrin.
We learned in organic.
The crown.
Crown structure.
Not the crown ether?
Crown ether.
Oh, I don't know, because I didn't teach that part to you. This is not an ether, though. You look. This is not. This is called a porphyrin
It
ring.
just like held a metal or something inside.
Yeah, this is not an ether. All right. This is considered a prosthetic device in the sense that it's bound so tightly that it's hard to actually get it out. Or sometimes they're actually they can be incorporated into the actual covalently bound to the structure. All right.
Like the crown thing.
So, quaternary structure, we've already talked about it, how we have multiple protein monomers coming together, or once again, you can have the nucleic acid protein coming together to form an active structure. This is the kind of terminology that we see. These are enzymes that we will see at some point in time, either this semester or next semester. Whoops, wrong one. And this is called a dimer, whereas hemoglobin is actually called a dimer of dimers, because and sometimes they write it out as a 2+2, because there are 4 subunits, but there are 2 that they call alpha subunits and 2 that they call beta subunits, even though they're all alpha helical in structure. I don't know why they just like to utilize alpha and beta in the Greek letters a lot, but that's just the way it is. Of course, the insulin has 6 subunits, but they can go way, way, way up high. For example, in neurochemistry, recently we were talking about ferritin that had 24 subunits, so they can be huge. All right. When the video last left off, it was talking really about the oxygen binding of hemoglobin and the fact that this is called cooperative binding. The binding of the first one is the hardest. Right? Whereas myoglobin, there's only 1 subunit, so there's no cooperativity. By definition, you cannot have cooperativity because it's either bound or it's not bound. Right? Oh, a little blurb. Next semester, we will be offering enzymology, and it should count as either a biology specialization or a chemistry specialization class for you if you want to take it. And it's going to be taught specifically with those, with the idea of medical school or medical backgrounds and stuff. So we go a little bit more into some like why this is important and like binding in particular, which we don't get a chance to get into that, and all that kind of stuff, enzyme mechanisms. In case anyone would like to take it, it should be offered next semester. All right, this is just made me think of it. All right, so one thing that changes is the structure of hemoglobin or myoglobin for that matter, but the structure changes upon oxygen binding. And that's the reason why it becomes cooperative. So what that means, and this is the important thing, the take-home message from it. Let me draw it. You're going to see these curves a lot. That's a straight line, even though you can't tell it. All right, so they like to use theta. And then on the bottom, the x-axis is going to be a concentration of something. Of course, for hemoglobin and myoglobin, it's going to be oxygen. It can be either in molar concentration, or since oxygen is a gas, it's going to be partial pressure. There's a little p. It doesn't really matter as long as you put something in. I just wanted to let you know. So this is some type of concentration. Oh, I did not mean to do that. All right, so here, I'm going to do it as concentration of O2 because that's what I'm used See, but don't be alarmed if it says partial pressure of O2. It doesn't really matter. It's just a concentration unit. Theta literally means it's the fraction or percent bound. Sometimes they call it degree of saturation. So it matters. It doesn't matter to me if you want to do it as a fraction bound or if you want to do it as percent bound. The only thing that matters is if you do a percent, it's going to go from 0 to 100. If you do fraction, it goes from 0 to 1. Okay, so that's why I have it here. It's going to go from 0 to 1 as a fraction. Whereas if you did it as a percent, it's going to be from 0 to 100%. Okay. I'm going to do myoglobin first. So this is what myoglobin looks like. This is not necessarily drawn to scale. Definitely not drawn to scale. You'll see a better picture in just a moment. Myoglobin, I'm going to abbreviate as MB. That's what a lot of... Okay. Whereas hemoglobin looks a lot different. So the binding, so at really low concentrations, it's hard to bind hemoglobin. Or I should say it's hard for hemoglobin to bind oxygen. As that first one binds, it changes the conformation of that subunit it binds to, which alters the structure of the two neighboring subunits. And so it becomes faster and faster and faster, and so it looks like this. I will say at any given concentration of oxygen, the binding of hemoglobin is lower than that of myoglobin. Assuming that it's all wild type. So that's hemoglobin. Now, this is the important part. I do not know if they, and notice it doesn't go up to 1 or 100%. You can never, it's never truly 100% bound, typically. That's why if you notice whenever they do little sensors, I mean, very rarely would it ever say 100% oxygen saturation is what I'm measuring. And if it did, it's probably because it's not that sensitive, and it's really probably like 99%. But it's just the asymptote. If you think back to calculus, this is the asymptote that's approaching. Okay, does anyone know from calculus, what's the structure, what's the shape called for myoglobin? When there's no lag, it goes up and it makes this, it's very important. The term. What is that shape called? This isn't a log plot, though. It's hyperbolic. This is a hyperbolic graph. So it's a hyperbolic relationship. What about the one for hemoglobin? What's that shape, that kind of graph called? Where there's a lag or a delay, and then it becomes, so what it is, it's hard for it to bind, and then it gets really, really easy to bind, and then it's almost all bound, essentially. Does anyone know what's this one called? What's this plot? What does it look like? I would just ignore that. If it was a letter, the alphabet, what letter would it be? S. And this is called a sigmoidal plot. A sigmoidal relationship. Some people even will talk about the sigmoidicity of something. This is so sigmoid. Sigma comes from the term sigma for S. The reason why I say that is for these binding curves. This is a binding curve. If you see any type of sigmoidal plot or sigmoidicity, it means that there's a cooperative relationship. This means it has to be. I mean, that's what it's indicative for binding. This is a cooperative. And this one in particular is positive cooperativity. Well, that'll make more sense in a moment. Just because the binding of the first one makes it easier for the second one to bind, which makes it easier for the third and the fourth, and so on and so forth. Hemoglobin's only got 4. We do a lot with these binding curves. So we're going to talk by the end of this chapter a little like the fetal hemoglobin. The fetal hemoglobin is a different isoform, so it looks different. The shape of hemoglobin depends upon things like the 2,3-bisphosphoglycerate that's bound, or chloride and things like that. As we talk about in greater detail. It's always important here, the 50%, or once again, if you're using fraction bound, it's 0.5. That's a lot of times the comparison that they use. It is related to KD. For those who've started doing that for their enzymes and stuff. So that's why if we look, once again, this is not drawn to scale. But this is what they many times the dissociation constant, or the KD, is what they're comparing when they talk about affinity of something. So if it's tighter bound, it's going to have a much lower, what that means is literally it takes a much lower concentration for it to get at least 50% bound. Okay, and so we can see here myoglobin is always going to be less than that of hemoglobin. That's because, once again, it's either on or off, because there's this one subunit. So if it's a hyperbolic graphs typically are indicative of no cooperativity. Okay, or just being one subunit. But there are times that you have something that's more than one subunit, and it doesn't matter. It's not cooperative. They're doing their own thing, and so then their binding curve would be hyperbolic. Okay. So this is the oxygen binding hemoglobin. This is just a better picture. Notice they use partial pressures. It doesn't really matter. Oh, one thing I forgot to point out. Let me go back. That's why I just wanted to point that out, because here. So once again, sigmoidal curve is indicative of cooperativity. Another term that they like to use is called allostery, which I'm pretty sure I used that on the whoops. So allostery, and once again, you can be either positive or negative. Same thing. I know it seems counterintuitive, but cooperativity doesn't always have to be a positive. Okay. Usually it's what we're talking about. There are times in feedback condition where it's actually negative cooperativity. Negative allostery.
So the graph would be just integrated.
Pardon?
If it was a negative, the graph would look like a backwards S.
Well, literally, it would make it, the slope would be decreasing. So let's see, it would probably look like myoglobin in the beginning, right? You could bind it really easily, and then the second or the third binding or whatever would start to decrease. So there's what we get this whole term. These are allosteric. Once again, we're usually talking with respect to quaternary interactions. So we can have things that are either activators, or if they have negative aspects, and they're called inhibitors. Homotropic versus heterotropic just means that it's regulated by its normal substrate or ligand, whereas hetero means it's done by some other non-substrate or ligand. Okay, and I think later on I've got ATCase coming up. Allosteric effector just means that it's going to cause some type of cooperativity. Okay. And there are two, wait a minute, where's the next one? Whoops. There are two models to this behavior of allosteric enzymes. One's called the concerted, and one's called the sequential model. And we're going to go into greater details for that. Okay. So, just because I want to, here we go. They do use similar terms. They like to do R and T. And so R usually stands for relaxed. So the whole idea for these models is that there are two forms. There's this R form or the T form. T structure, R structure, or T structure. T, I've seen it referred to as multiple things. Some say it's tight. Some say it's tense. Some say it's taut, like, like a taut rope. Not taut as in I'm teaching you. The whole purpose of it here is when we're talking about a substrate, remember, or ligand, the binding of the substrate or the ligand, it's easier for it to bind to the R. So binding is easier. And binding is more difficult in the T. So binding is by default. In the T state, binding is going to be more difficult. All right, so what does this mean? What does this look like? This is just what I've been saying. So the conserved model, the way that it works is the enzyme exists in either the T form or the R form. Usually, if there's no substrate around, it's going to be in the T form. And once the substrate or the ligand binds, it's going to cause all of the subunits to immediately go to the other form. So it's like an all and none. And it means that, this is the important part, that all whoa, what happened there? Sorry. All subunits change simultaneously. Conformation is just a fancy word for shape or structure. So now I'm going to make this a little bit more, not complicated, a little bit more detailed than what is shown in the figures on the PowerPoint and in the book. Just because it helped me think about it. So let's do the concerted model. I'm only going to do something, there are only two forms. This is the concerted model once again, so you want to write that somewhere up. Okay. And it's just easier for me to write out R's and T's, whereas a lot of times they do like little circles and squares or little different shapes and things like that. All right, so what it means is obviously there has to be at least two subunits. So I'm only going to do two subunits. We're either going to have it in the where both subunits are R, or, and there's an equilibrium. Whoops, that's supposed to be an equilibrium. That is a really crappy equilibrium sign. Or they're both in T. Okay, that's it. Those are the two possibilities. And according to the concerted model, is once a substrate binds, or a ligand, because technically substrates are specifically, usually we're using that with respect to an enzyme, because ligand can be down. So I'm going to call it substrate S, but your book may use an L. Some books use L, some use S's. What it does is it binds preferentially to the R, and by the binding, when this substrate binds to this R, yeah, it's going to cause a new equilibrium. And by definition, another substrate combines, so on and so forth. So if we go back to Le Chatelier's principle, all the way back to Gin Chem, Le Chatelier, remember he's the one that says, you have something in equilibrium. When you disturb that equilibrium, it's going to try to make up for it, right? To reach the equilibrium once again. So what do you suppose is going to happen whenever this substrate comes and binds to the R's here and it forces the equilibrium this way? What do you suppose is going to be happening to the T's? What's going to happen to this equilibrium? We're going to shift towards the T. So, and I'm going to make these numbers up because it's going to depend. Let's say before it was 50-50. We had a substrate, it doesn't really matter, 50-50. We had substrates come and bind, and it took one of these away. So now there are less R's and T's. What do you suppose is going to happen? it's going to shift it to the left here. It's going to go from the T's, we're going to turn into the R's to try to reacclimate. Maybe the 1-to-1's not the best one, but you know, what's going to happen is it's going to force the equilibrium towards the left. However, let's say that we have something that likes to bind to the T state. I'm going to call it an inhibitor. Ooh. So since it likes to bind to this T state, it's going to look like this. Whenever an inhibitor binds, what do you suppose it's going to do to the equilibrium? It's going to pull some of it over towards the T side. Just like there's also some, what if it's not a substrate? What if it's just an activator? You can think of the same thing. Here's, I don't have another color, but we could have had something that maybe it's not a substrate, but it's just an activator that likes to bind to the R's. Then it's going to be the same thing. It's just that perhaps now what's going to happen is you can have substrates come down here and bind this, because it can't be inhibiting that, because otherwise it's going to be competitor. But substrate can go ahead and come here, but it's going to pull stuff this way. So activators and substrates, they like the R group, not R groups. They like the R conformation, so they're going to pull it this direction. Inhibitors like the T conformation, so they're going to pull it that way. But it's all or none. Okay? That's why those are your only two options. Notice we don't have it an R and a T, where one subunit is R and one subunit is T. Okay, because this is concerted. When one changes, the other one changes. Okay, so let's see, like, some noise that they show. Here, let me make it smaller. This is the exact same thing. Once again, they're showing it as a dimeric protein. See, it's got all these little nifty little shapes. This is the old book. I do not know why they use the term L. Normally we use equilibrium constants of K. Okay, so that would be a K. Otherwise it's all the same. So your book calls it a K. I will always call it a K, but the old book used L. All right. And so without the substrate binding, more of the enzyme is going to be in the T state, or more of the protein is going to be in the T state than the R state. And so that's why the equilibrium constant, remember it's always products over reactants, the equilibrium constant is going to be really big towards favoring the T. Whereas once you bind the substrate, since it likes to bind R, it's going to pull the equilibrium this way. And so it's going to decrease that apparent, it's going to perturb it from equilibrium. So then some of the T's will become R's. That's all or none. Okay. So now the sequential model is where each subunit changes R to T on its own. Okay. Sequentially. It's called, many times they call it the induced fit. Okay. Which later on, probably not until next chapter, we'll talk about an induced fit model of enzyme binding substrate and how, and if you take enzymology, how that's not quite 100% right. Okay, a lot of books will just say induced fit and that's it. I think this book, your book, will go into a little bit, but it's not, I'll tell you the reasons why it's not 100% right. But it's more right than the lock and key, usually. So let me draw what that looks like using my R's and T's. So once again, we're just going to do two subunits. So we have, and it doesn't matter, let me just do RR. RT, TT. So that's before we get into any substrates, activators, inhibitors. You can see it's going to become multidimensional. But it's sequential. So what happens is here, we can add in a substrate binding. So now it looks like this. okay, which can then go to this. That's just one substrate. You can imagine there can be activators, which if I wanted to put an activator on this and draw it correctly, it would actually be in a third dimension, okay? Which I'm not going to try to draw that. If you drew the activator going up, that'd be fine. But in theory, an activator shouldn't be affecting substrate binding, so you can imagine. Actually, it's easier for me to show it on here than on that there. Where an activator binds here to make an RA coming out here, then the substrate binding can make RAS, and then going on to make RAS/R, and so on and so forth. That's why I say it could be a third dimension. Or you can just show it as an activator and then try to one substrate. Okay. Whereas an inhibitor, of course, where do you suppose the inhibitor is going to bind? It's going to bind. I'm going to show it right here, just because I'm running out of. It binds to the T state. So therefore, it's going to help pull everything in this direction. But that's why it becomes more complicated. For more enzymes, this one probably does a better job of explaining what happens. It's not to say that there aren't any that do the concerted method, but sequential explains. Hemoglobin is concerted. It's not an enzyme. But we're going to see hemoglobin in just a minute, and see how it becomes much more complicated. But once again, you can even imagine, in theory at least, where we could have an inhibitor bind to this T, which would help pull it this direction as well. Okay, and that's at least in theory. And like I said, they can become much more complicated to where we can have things coming out towards us in a third dimension and so on and so forth. Alrighty, so this is the simple sequential model. It's not showing any inhibitors. You can see it binding, how it's transforming it, causes it to go to the R state and pulling it towards the R. Alright. So, this is hemoglobin. Remember, hemoglobin's got 4. Yeah.
Are these just different theories of how enzymes and substrate?
These are different models to explain enzyme, or even hemoglobin. Hemoglobin's not an enzyme, or just protein binding.
So, no, which one's right? They don't know, or what's?
No, it's not one answer to all proteins.
Each protein has its
Could
own.
possibly be different. Mm-hmm. Yeah. For hemoglobin, I'll explain it in just a moment, but it can be different. This is let me make it smaller. Here's hemoglobin. So here's where they're using ligand, because technically ligand, because the oxygen is not being catalyzed. What?
Are you memorizing this?
You should not memorize it, but you should understand the logic behind it. See, this right here, I don't remember, I think it's the square, now I don't even really remember. I think that the circles are supposed to be the R versus the T. That part doesn't really matter so much. But if you notice, I'm going to call this one R and this one's T. It's either all or none. It's either all circle or all square. And so the binding of the first one, if this is the R, the binding of the first ligand makes it easier for them all to become circles, which makes it easier for the second one to bind, and so on and so forth. Okay. Whereas if it's the concerted one, it's one step at a time. Okay. So actually, I may head backwards where the circles are the T's and the squares are the R's. It doesn't really, like I said, it doesn't matter which one, as long as you defined it. Whereas, let's say this is where it's really hard to bind. It binds that first one, which changes the shape, which makes it easier to bind the second one, which changes the shape. It makes it easier to bind the third one, changes the shape. It makes it easier to bind the fourth one to change the shape. So this one does a better job of explaining hemoglobin versus this one, because the four different subunits change independently. It's not all or none. Myoglobin is all or none. Of course, it's only got one subunit. But if hemoglobin looked like this, it would all go from being the all going from being the T to the R state immediately, the binding the very first one. And so it wouldn't be a really good sigmoidal curve, a really steep sigmoid. It would be more steep sigmoidal curve than what it really is. Okay. Oh, I thought I put these in different order, but I did not. Okay. I was going to jump the gun. Just because I'm so excited. All right, so the oxygen binding and hemoglobin. Now we're going to talk a little bit about the Bohr effects, which I know one year for the MCAT, Bohr effect is one of the specific questions. I know it's one of the topics that's listed down on the possible topics list that they send out every year. Alrighty. This one, you really need to just kind of talk yourself through it. Right, so I give everybody a moment to get caught up. This is the way to explain pH and the effect that pH has on hemoglobin. So, let's see. The best way to start this off. I guess it doesn't really matter which one that we start off with, but I'm going to start with the left, just because going left, we're used to reading things left to right. This is hemoglobin with bound oxygen. So therefore, if you have a lot of H pluses around, those H pluses compete for the oxygen binding. So the protons will bind the hemoglobin and release oxygen. So that's what that means right here. So now we have to put this with respect to pH. And just remember, pH is equal to what, if you're going to write it out mathematically? Negative log base 10 of concentration of H plus. So therefore, if this is high, the concentration is high, what's happening to pH? As the concentration increases, is pH going to increase or decrease? It decreases. That's usually the mistake that people make. Okay, right, that right there. Because remember, it's negative log. So therefore, parts of your body that have lower pHs, will the oxygen bound or will the oxygen be released? It's released. Okay. So the parts of your body that's going to be more likely to bind oxygen to the hemoglobin will have a relatively higher pH than the parts of your body where the oxygen needs to be released. The buffer system, there are two main buffer systems in your body. There's more than two, but the two main ones are the carbonic buffer system, carbonate, based off of carbon dioxide, and that one's in your blood. Okay. What's the buffer system that's primarily used in your cells in the cytosol? It's phosphate. Okay, those are the two ones that we'll see over and over and over again. There's also phosphocreatine and creatine and things like that. So there are some other buffer systems, but those are the two main ones. This one that we're right here that we're talking about, and then phosphate, which is within your within the cells in the cytosol typically. So how does this relate to carbon dioxide? Carbon dioxide is a gas, right? That's the reason why I didn't have a can of pop. I always say that when I bring a can of soda or a can of pop in, because it's carbonated, it's got carbon dioxide in it, and so it's under pressure, so the carbon dioxide gas stays in solution. But the moment you release it, or you open up the lid, it goes psh, because it releases the gas, and more of it becomes insoluble. So carbon dioxide, which where do we get carbon dioxide? What is carbon dioxide in vivo the result of? Pardon? That's one possible. It's just the extent is it's the ultimate product of metabolism. It's a fully oxidized carbon. That's where you've taken your fat or your glucose or whatever, you've taken that carbon and you've used up every possible electron you can get from that carbon. That's as oxidized as carbon gets. Okay, so we've got to get rid of it, otherwise we would die. And plus, if we're going to get rid of it, why don't we use it to our advantage, so to speak. So it's a brilliant handiwork of God, since we're a Christian university. So the carbon dioxide cannot just be a gas in your body, otherwise it would balloon up and decomposing gases balloon up and you would explode. So what happens is whenever it's in water, we've got an enzyme called carbonic anhydrase. It's a zinc metal enzyme. And my boss, actually, this is what made her world famous, the one that I got my PhD through, because what it does is it converts carbon dioxide into water, carbonic anhydrase does, and it turns it to carbonic acid. Okay, then carbonic acid doesn't stay like this form. It turns into bicarbonate, which is relatively benign, and the hydrogen. So therefore, what this means are that areas that have a higher concentration of carbon dioxide. So since there's a lot of CO2 around, you go according to Le Chatelier's principle, it's going to go this direction, which is going to go this direction. Technically, there are two steps. It means that you're going to have a higher concentration of H+. If you have a higher concentration of H+, you're going to have a lower pH. It also means that it's going to be more likely that when hemoglobin gets there, it's going to release its oxygen. So now we think about this, logically speaking. You're working out. You're feeling the burn, you're feeling the burn. Okay, what's happening to your muscles? Don't make me keep on doing this, because I will feel the burn. So what's building up inside your muscles? What's one of the side products that's building up inside your muscles? Lactic acid, one of them, if you're really going into anaerobic conditions. But just carbon dioxide in general, because it's being metabolized, right? So because of that, the pH is decreasing in your muscles. So therefore, you want your body to take the hemoglobin from your lungs, where the pH is much higher, and oxygen binds, takes it here to your muscles, whatever muscle it is, where the pH is lower, it releases the oxygen to bind, and then helps it break up the byproducts. And so that's what this is. This is the one from their older book, but it just didn't go through the logic behind it. It's easy, more simple to show, but it doesn't really explain the more effects in each step. Okay? This is a little table saying the exact same thing that I just went over. Except I did not make this table, so I apologize for the fact that if you notice the subscripts, I don't know. What happened is throughout the various iterations of PowerPoint, and it won't let me go in and fix it. So the subscripts and the superscripts got separated from your parent letter, but I think you can understand it. All right. So also speaking, I kind of went over a little bit of this. You're going to see the phosphoglycerate derivatives a lot. Right? Typically, if you're healthy, hemoglobin in your blood is going to be bound to BPG. BPG, what is it? You may not understand the term glycolytic intermediate. What does that mean, glycolytic intermediate? Does anyone know? What does glycolytic mean? So it's sugar. It does. So what metabolic pathway breaks down sugar typically? Glycolysis. Glycolytic intermediate. Which I haven't caught that, even though I used this for years. Remember, in the old days, several years ago, biochemistry used to be one semester, so we covered glycolysis the same. Okay. All right. That's why I probably would understand. But no, it is, you're going to find out. BPG comes from glycolysis, okay? Or it's the glycolytic intermediate you can get from glycolysis. So if we're just given this information below, this is what BPG looks like, 2,3-bisphosphoglycerate. As long as you know what glycerol is, you can actually work backwards to figure out what glycerate is in the 2,3-bisphospho part. You just add in phosphates. You're going to learn how to do glycerol. What does glycerol look like? You should know the structure of glycerol right now already. How many carbons are in glycerol? 3. And what's so special about glycerol? Glycerol, R-O-L. Yes, there's an alcohol in every single one. So in organic chemistry, you call it 1,2,3 propane triol. The rest of it's hydrogens. So glycerate just means that you convert one of these, this right here, into the carboxylate, and then bisphosphate just means you add phosphates instead of these two hydrogens. That's why, as long as you're gonna next semester, that's why if you know this right now, it's gonna be help next semester. Okay, but just give that structure below. What kind of amino acids and hemoglobin do you think is going to bind to BPG? Pardon? Positively charged, and so what are they? Right, so what are they? Lysine, histine, and arginine, especially lysine, arginine, hemoglobin. All right, and so what happens here, BPG, so the way that, this is hemoglobin. Oh, I probably should have used two different colors. But even though it's all alpha helical, they call two of the subunits alpha and two of the subunits beta. Okay, but it's all alpha helical. BPG binds between the beta subunits of it when it's in the T state, and it stabilizes the T state. Okay, so what do you suppose that means?
Is it activated?
It stabilizes the T state. So which one binds easier, R state or T state? R. So if it's stabilizing the T state, is it going to increase the ability of oxygen to bind or decrease the ability of oxygen to bind? Decreases it. Okay. So why is that important? Okay, so first of all, what that means is BPG actually, another way to think about decreasing its ability to bind means it's increasing its ability to come off, okay? And so BPG actually promotes oxygen dissociation to the point where if you remove BPG, your hemoglobin actually has problems getting rid of oxygen. Why would that be bad? What would happen to you? You're going to die, right? You're going to have problems getting oxygen to the muscles and the parts of your body that needs it. So that's the reason why, once again, you're going to come up and you can start to draw, let me make it smaller, the saturation curves. And that's what a lot of this kind of stuff is. Whoops, sorry. The numbers aren't so much important. That's not CO. That's supposed to be a concentration. I'm just in a hurry. This is hemoglobin. You'd make hemoglobin sigmoidal. So if you do not have BPG, is it going to shift to the left or shift to the right? So if you just read, if without BPG, is it going to shift it to the left or shift it to the right? It's going to shift it to the left and make it more hyperbolic. So this is without BPG. And at high concentrations, it's good, it's going to even make it more like that. So high BPG concentrations. Because there's actually also a binding constant, equilibrium constant for BPG binding. It's going to shift it to the right. So this is the kind of logic that you have to use a lot when you're starting to think about this. And like why it makes sense. What this means is that, I'm just going to look at the one that says high BPG, is that let's assume that you've got a lot of BPG around. What that means is that as it gets to tissues and the oxygen concentration in that tissue decreases, it makes it easier for the hemoglobin to release the oxygen to help out that tissue. If you didn't have BPG, you would literally, I forgot to put in. See, this is like the 50% mark. So you can go down to see like where the concentration is for each one of these. you would literally have to starve yourself or starve that tissue of oxygen to where the concentration got really, 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 really low before it would be able to release it. Okay, so that's how BPG helps. And there are different mutations. You can imagine, like we could write, and there are known mutations out there, lots of variants to hemoglobin. Say, what happens if you have such and such a mutation that decreases the ability or decreases the binding of BPG? That means it's going to shift the curve to the left. Whereas if you, in theory, had one that stabilized BPG binding, then it's going to shift it to the right. This is actually what I just drew, but it looks neater. Okay, so that's why you need to be able to explain this kind of thing. Okay, so what they're showing, this is the partial pressure. This is the amount of oxygen that there are in most tissues versus the amount of oxygen that's in the lungs. Here, Florida is pretty much sea level. So since we're here at Florida, we are almost fully saturated. That's why if you're a healthy individual, you should have, and you go get your pulse ox, measured, it should be really high here in Florida. So what happens though is as it gets to the tissues, so it goes from here to here, it goes from being almost 100% bound to only like approximately about 60% bound, 0.6 or so. So it decreases, gives up like 40% of the oxygen that's bound on the hemoglobin. Whereas if you didn't have the BPG, it would go from 100% bound and it would still be 100% bound. And so we would die. Okay, so that's why you need BPG around to bind to our hemoglobin. Because at this concentration, which is the normal concentration of oxygen in those tissues that are working out, it would still be almost simply 100% bound. This is also the reason why, and this is always very important too, that you need to explain if myoglobin is so good and efficient at binding and binds when these oxygen, it doesn't do this. Why are we not myoglobin bound? Why are we not myoglobin based? Why are we primarily hemoglobin based? And there are organisms that have more myoglobin than we do. And also, what tissues of our body has higher concentrations of myoglobin? So why use myoglobin around at all? So, or why don't we only use myoglobin? Why use hemoglobin at all? So that's the kind of thing you need to think about before Monday. Okay, so I'm going to go ahead and